What's the enzyme that takes the NAD to NADP?
This one? What?
NAD to NADP? When does it get phosphorylated?
It doesn't. I mean, it does elsewhere in the synthesis. NADH, right? Electrons are taken away from NADH when malate is reduced. Those electrons are given to NADP when it's oxidized. Right? So it's a transfer of electron equivalents. Okay? We good with that? All right. So there's our transport out. Now,
This kind of might be a dumb question. So is the only difference between NAD and NADPH that the last one is phosphorylated? Is that the difference?
yes, the only difference, and so what difference does that make?
It's a high energy bond it can break.
No, it's because it's a phosphoester bond, so it's not that high energy.
Enzymes recognize one or the other.
Enzymes recognize one or the other, so it creates really two distinct pools of reducing equivalents. One whose intent is to make ATP, NADH, the other one that's used in biosynthetic reactions. So those two pools are independently controlled. This is one of the few places where we see this kind of interconversion. And there's another one, a couple of other places, but for the most part, enzymes that use NAD don't use NADP.
And is it NADP that's used for biosynthesis mostly, or is it the NAD? 'Cause you said,
NADP,
okay.
right, NADPH. Okay? So, now we said that our donor group was a 3-carbon molecule. So now that we've got the acetyl-CoA in the cytoplasm, we have to carboxylate it. Right? So we have to carboxylate it. And we have a standard type carboxylation reaction. We got bicarbonate and ATP. We use the coenzyme biotin, right? The ATP activates the bicarbonate. You get a phospho or a mixed anhydride bond. Biotin then can act as nucleophile. It ends up with the carbon dioxide as a carboxylate. Then acetyl-CoA comes in. Right? This site is deprotonated. It can take the carboxylate, and you get this 3-carbon malonyl-CoA. Right? So that's the malonyl-CoA. Okay? So, let's see. There's a phosphopantothene. What other thing have we talked about that uses pantothenic acid? What other molecule has pantothenic acid in it? Well, it's another molecule that has a thiol. What's our other big thiol molecule that we talk about? Usually we leave everything off except this.
Like cysteine or like methionine?
Yeah, that one. Huh? Yeah, no. No, you're making it way too hard.
Methionine?
Yeah, well here it is. So, in the acyl carrier protein is a phosphopantothene group that looks like the phosphopantothene group of coenzyme A. So the acyl carrier protein has a group that looks like CoA. The only difference is instead of being attached to an adenosine, it's attached to a serine of the acyl carrier protein. Okay? So, here we go. We end up, the malonyl group gets transferred in a transesterification reaction to the acyl carrier protein, right? CoA leaves, acyl carrier protein accepts it. Okay. So, on the acyl carrier protein, right, this is still a carboxyl with a carbonyl. That's susceptible to spontaneous decarboxylation. So on the acyl carrier protein, this decarboxylates, and we get this kind of active group. Okay? Now, right? On another cysteine of the fatty acid synthase complex, there's the keto-acyl-CoA synthase, right? So we're going to create a keto-acyl group. So when this decarboxylates, it creates a carbanion. That carbanion can attack the carbonyl of the acyl group on the keto-acyl synthase. Right? You get a, what kind of reaction would this be? Nucleophilic acyl substitution. What's our leaving group? Yeah, that thing, what is it? The cysteine of the ketoacyl synthase is the leaving group. And so we create a beta carbonyl, right? A beta carboxyl, or I'm sorry, a beta carbonyl, a beta oxo, a beta keto, that's the word I'm looking for, a beta keto intermediate, okay?
You said it like 11 times, but what is KS?
The ketoacyl synthase, right?
Oh, so it's an enzyme?
Yeah, the fatty acid synthase is a multi-enzyme complex, or a multi-protein complex. So there's the acyl carrier protein, then there's the ketoacyl synthase. Okay? So, okay, so that gets us to here. What? Well, that's why I gave you the slides, right? Right, Jackie?
They only do so much.
It's all on there, isn't it? Okay, let's see, can I make it bigger?
No, I'm not talking about the size. I'm saying it's just taking a long time to get through all the steps. There's a lot of steps.
Yeah, there's a lot of steps. Okay?
We're still on synthesis, right?
We're still in synthesis, yeah.
Just checking.
Okay, so,
Oh, sorry.
let's see. So now we're down to here, right? Our acyl carrier protein, the acetyl-CoA, attacked the acetyl group that was on the ketoacyl synthase. We end up here, right? We've brought two together.
Is that bottom molecule still considered an acid anhydride or no, because it has a sulfur attached to it?
What is it? So what is it? What is it?
Thioester.
Thioester, right? So we have a thioester. Okay, so now we're here. So we're still on the acyl carrier protein. So within that complex, there is a reductase. So we bring in NADH. NADH reduces our carbonyl to an alcohol, right? We're doing essentially the reverse of fatty acid oxidation. I don't know what they're doing up there, but it was something around a construction zone.
I don't think the board's going to help. It's like coming from the wall.
No, it's coming from them. They're working over on the door. So, right? So we reduce it using NADH. Then we've got our alcohol. We do an elimination, right? So there's a dehydrase as part of this complex. We do the elimination, get the conjugated butynyl-CoA, then in a nucleophilic conjugate addition, better known as a Michael type addition, the hydride from NADPH is directed to the beta carbon, making a carbanion on the alpha carbon. That is protonated, and we end up with our reduced acyl group still on the acyl carrier protein. That is then transferred back to the ketoacyl synthase, and the new malonyl-CoA comes in and is added to the ketoacyl protein, and away we go. Right? So we just keep doing this a cycle at a time.
They're just building a chain.
Building the chain. Right? And so usually, if you look at biological systems, at least mammalian systems, this cycle works until you get to palmitate. Right? This, in the cytoplasm, works till you get to palmitate. How many carbons are there in palmitate? 134? No. No. That's stearate.
Oh, it's not 134?
It's not 134.
I was like, wow, this has been going for a long time.
What is it? 16. Okay? Beyond that, further elongation, and if necessary, desaturation, where do those occur? Can you see around Nikki's water bottle?
More or less.
Okay. Where do those occur? When in doubt, what are you supposed to guess when you're guessing subcellular locations for odd events?
The liver.
No, the liver is the organ you guess.
Oh.
If you're within a cell.
Mitochondria.
No.
Cytoplasm.
No.
11.
No.
Membrane.
No. What membrane?
The intermitochondrial membrane.
No. Lots of weird stuff happens here. When in doubt, guess this. Right?
Lysosome.
No.
Oh.
When in doubt, guess endoplasmic reticulum.
I don't think you've ever told us that.
Huh?
You said that like 6 times and you said no.
No, nobody said endoplasmic reticulum. At least not loud enough that I could hear it. I get a lot of mumbling. Remember, I'm aged. You have to talk loudly and clearly for me to hear it.
No.
No, they kept saying mitochondrion and, right?
We were wrong.
So, right? So that continues. We get 7 reaction cycles to get the palmitoyl acyl carrier protein. When you get the palmitate, the thioester is hydrolyzed, that is released as palmitate. Any further elongation and desaturation occurs in the endoplasmic reticulum.
Are we going to talk about how that occurs?
We're going to talk a little bit about how it occurs. Depends on how it's going. I'm running out of time though.
Is there a reason why it can't all be done in one place?
I don't know what the reasoning, the metabolic reasoning is for stopping at 16 and moving to other processes beyond 16. Let's see.
So is there a special transporter for that to get it out then?
No.
Or in, sorry.
Well, it's a lipid. I don't know how those lipids get into the endoplasmic reticulum. There has to be a way because they do. But I don't know what it is.
Maybe that's why they stopped there, because that's the only one that has a transporter.
Yeah. So this is a layout of the peptide of the fatty acid synthase complex. Right? It's sort of a complex thing, right? So this is the acyl carrier protein part. This is the ketoacyl reductase. This is the dehydrogenase. This is responsible for interaction of the dimers with each other. This is the ketoacyl synthase. What's MAT? The malonyl the malonyl transferase. Yeah. So let's see. I like this. What's this?